record. What is this? 10:05. All right. All right. Hey, and I'll say this. I know it's only the two of you right now, but if you got a question, and maybe particularly for you, James, throw it up in the chat so that when I run out of questions from Eli here, I'll know which ones you have and make sure you're in front of whomever else pops in here. So I'll keep it going. All right, Eli, what can I do? What questions did you have?
All right, so my first question is about number 6 in chapter 4.
Okay. Oh, and let me give me just a second here to also set up. Let's see. I'm going to call up the homework for your class because you said number 6, chapter 4, right? Or did I get that backwards?
No, that's correct.
All right. So I'm going to write down here chapter 4, number 6 on my little paper. 102, chapter 4, number 6, write it twice. And let me scan down here. All right. Go ahead. Fire your question. I think I got it in front of me now.
Okay, so it's got A, B, C, and D, correct? And the one I was having issues with was B, which was how to determine the circular change in velocity, which I was reading through the textbook and I couldn't really find anything on that.
Perfect. Yeah. Okay, so here's what I'm going to do. I'm going to connect or share my screen here so I can have a little piece of paper. And let's talk about that. And it sounds like you've done most of it, but just for the sake of other students, let me run through each of the options here.
Totally.
Okay, so when it says here a child rides on a carousel, what is the direction of each of the following? So the first one says the velocity. And remind me again, which one did you say was your problem?
B.
B. Okay, so I'll do A, but maybe kind of quickly here. But I will say this: B, C, and D all really tie together in the same way, and that's how I kind of want to present it. So I'm going to draw a circle. Maybe here's the center of the circle. Maybe this would be the object that's going in a circle. In this case, it's a carousel. And so it's heading off in this direction. So A, which says the direction of the velocity, the velocity is tangential to the circle, which do the following vectors point. So, and again, sounds like you didn't have troubles with that. So I'll brush on that one really quickly. But let me skip your hardest one, which is B, and let me go to C for a second, because C is the acceleration. Now, numerically, it's equal to V squared over R. And just by the way you asked your question, you're not really asking about C. So I'm going to take from that you already know that the acceleration is towards the center of the circle. That was one of the things that good. I hope the book emphasized, and I tried to emphasize by spinning the little racquetball on the string there. Yeah. And then if you know that much, then watch what I'm going to do for D, because I think that'll help us with B. So in D, I'm going to say here, Newton's second law says the net force equals some number times A. Now, there's something I should emphasize in this math. This math not only says that the magnitude of the net force is equal to the product of these two, but it's saying also the direction is the same. So this is saying the force and the acceleration are in the same direction. And I think that's kind of how I answered it in class, because I was spinning this ball on the end of a string. And really my argument was the string was tugging on it. So my argument was more about what is the direction of the force. And I used then really this connection that says that the directions are the same. And I want to emphasize that because it's easy for the beginning student to just look at this and say, well, the numbers multiply out, and forget totally about that it's also saying direction. And so there's a little arrowhead we like to put on the above them to say, okay, the directions are the same too. All right, so now I'm going to use the definition of acceleration, which is the change in velocity over time. And notice the same kind of logic I'm going to use is, again, most students, when they begin a physics class, just see this as an equation that the numbers match. And it's true, the numbers do match, but also there's little arrowheads over here. There is a direction. And so the direction to the change in velocity and the direction of the acceleration are actually the same. And so using that same argument, then I would say the change in velocity is the same as the acceleration, and the acceleration is the same as the force, and hence B, C, and D are all the same, and they're all towards the center of the circle.
Got it.
And yeah, and if you're good with that, I'll call it good. I can draw some more pictures here, but
No, that makes sense.
you know, so that's probably the best way to go through that one.
Okay.
All righty. Go ahead and shoot your other ones at me.
Let me find it. Oh, okay, so it's chapter 4 again. The exercise is number 1.
Okay. So exercise number 1, and this will be at 10:12. Okay, exercise 1. Let me jump back to this exercise 1. It says, find the size and the change in direction of the velocity for each of the following. Excellent. Now, again, I'm going to say the same thing. I don't know if you were talking about A, B, or C, but I'll also just say, let me run through all of them just because I think it's helpful for other students too to see each step, just in case they're stuck on something a little different than yours. But this actually ties really well with the one you just asked, where I said I was going to draw a picture. So I tell you what, I'm gonna backstep a little bit and actually draw the picture I was thinking about drawing. Well, let's say I did this. Let's say I just made kind of an old-fashioned number line, and I said, all right, get a different color here just so it stands out. What if I did something like this? What if I said, okay, here is the first number, the first vector. I'm going to draw a little green arrowhead, and it has some distance. In fact, maybe down here I should draw maybe an arrowhead that has length 3, and maybe an arrowhead that has length 4. Okay, now, for simplicity here, and it's going to get more complicated, I'm going to draw them in the same direction. But when you go to draw them this way, if you were to say, add the two together, a good visual picture is to say, well, draw the first one, and then wherever that ends, draw the second one. And so when you draw them head to tail, the total results is from the beginning of the first to the end of the last. Okay, so if I were to change the angle a little bit, and so maybe I were to say, okay, here is the 3, and maybe the 4 was off at a 90-degree angle. For visual effect, if I were to say, all right, add these two together, I would say, well, take the beginning of the first and then draw a line towards the end of the second one, because it's these two together, this 3 and this 4, that result in this combination. So we like to say something like this. We like to say, take vector number 1 and draw an arrow with it. Then take vector number 2 and draw an arrow with it. Now, if you'll let me write that in symbols, I'm going to do this. V1 for vector 1 and V2 for vector 2. And this right here is the sum of the two. So in green, I'm going to put V1 plus V2. Okay, now believe it or not, I'm actually getting to your question. All right, now watch this for a second. What if I were to switch the order? What if I were to start here at the beginning and draw V2 first and then V1? Well, I think you know that if you did 2 and first and then 1, you get the same thing as if you did 1 and then 2 first, right? Fair enough? And so I kind of have in red what we call a parallelogram, and the diagonal is the sum of the two. And so we like to call this the parallelogram picture. That, look, if you draw a parallelogram where, you know, the two parallel sides are the two vectors, the diagonal down the middle is the sum of the two. But here's my big question. What about, now maybe that one's too close to the same color. Let me get a blue here. What about the other diagonal on this parallelogram? What is it? Now, it would depend which way you pointed the arrowhead. So let me say, I'll draw the arrowhead from where the first one ended across the diagonal to where the second one ends. Now, the reason I'm doing that is I'm going to put a question mark here in the blue because I'm asking what really is this blue one? But I'm hoping you can see that this red number 1 and this blue question mark are drawn head to tail. So I would say number 1 plus question mark is number 2. Or put another way, question mark is 2 minus 1. Okay. So here's what I'm getting at, and here's how I'm going to answer your question. If you ever have a couple of vectors, first thing to do is to make a parallelogram. And the diagonal down one direction is the sum of the two. And the diagonal across the other part, that is from arrowhead to arrowhead. Okay? So drawing a line from arrowhead to arrowhead is the difference between them. Okay. So now let's come to your problem at hand. Okay, so your problem, number here, A, says something like this. Find the size and the direction of the change. All right, that's why it was so important for me to work up to this. Which one is the change? The sum is from the beginning of the first to the end of the second. But the difference, 2 minus 1, is an arrowhead that starts at the tip of arrowhead number 1 and goes to the tip of arrowhead number 2. Okay, so watch this picture. And I don't think this problem is two-dimensional in nature. I think these were all east and west. So watch this. If I say, find the size and the direction of the change in the velocity for each of the following initial and final velocities. So if I do kind of the standard grid where the y-axis is north, the x-axis is east, so never eat soggy waffles. Okay, so here's my compass rose. And if they say my initial is 5 west I'm going to draw an arrowhead pointing 5 steps west. So that's my initial, okay? And maybe I even should put the initial. And then it says to 10 west. Okay, so that I don't draw it on top of it and make it look kind of ugly, I'm going to draw a final kind of right below it. All right. Now, remember I said if I was at, oh, I should have put an F here for final, sorry. If I was adding them and I wanted to know what it would look like, I would draw the two on top of each other. So it would look something like this. I have enough room down here. I would draw, oh, my Zoom's acting funny. It's got like a little glitch.
I can see it okay.
Okay. I'll keep going. Tell me if it freezes completely.
Okay.
But if I were to draw the first one here, so call that V initial. And then where the first one ends, I will draw the second. Oops. And I guess I'm not real sure why I want to do that. That would be adding them. And I guess that just fits with my conversation. That's not what we want. Sorry. What I want, let me come back to my picture, is coming back here. I want to draw them so their beginning is at the same point, and I draw from head to head. So let me redraw. Okay, so here is initial, and maybe right next to it, I will draw final. Okay. But coming back to this story I was trying to tell you, if I were to draw from the end of the first one, so let me change colors and go, okay, from the end of the first one to the beginning of the second one right here, that little distance in my picture represents the difference. So I would say then I have drawn 5 west. Now, to be quite honest, since this is just a one-dimensional, I probably am making it harder than it might seem if you just did this. If you just wanted to say final minus initial, you might say, well, my final is, and using math, -10, because I have 10 pointing on the negative x-axis. And then I would subtract my initial, which would be a -5. Okay, so here's my -5. And then, of course, as you can see from the math, where 2 negatives make a positive, this comes out to be -5. So just doing math on a one-dimensional axis might be an easier way to come up with the number than these pictures. However, we don't always just have one dimension, and that's when the pictures are a little better. Now, let me go to part B, because again, I think we have the same story, where if I were to draw the first one, it would be 10 west, and the initial, I'm sorry, that is the initial. The initial is 10 west, and the final is 5 west. So if I use green, drawing from the end of the first one to the end of the second one, I would say I am drawing it a distance of 5, and it's in the eastern direction, a +1. So I would say 5 east. Now, again, let me do the numbers. If you would prefer to do this on a number line, since it's one-dimensional, this would be something like this. You would say, let's take final minus initial. The final, as they said, is 5 west. And again, labeling west as a negative, I'll put a negative, and then I will subtract the initial, which is 10 west. I'm using the negative for west. You can see that, again, 2 negatives make a positive, and you're going to get a +5. So that's how I would get the change, both in pictures and with numbers. And then C, I'm going to do the same thing. And again, it's one-dimensional. So they were really kind of kind to us. And I want to take this one step further here. But this says draw the initial, which, okay, would go, I'll do that in red. We'll go this way, 5 west. But the ending is way over here at 10 east. So if I were to draw an arrow from the end of the first one, the end of the second one, I would be drawing it a length of 15, and it would be to the east. And so the change there is a +15. And again, you can see that if you take the initial, it's final, which is +10, it's east, and minus the initial, which is a -5, you're going to get a +15. So again, if you just want to do pluses and minuses for east and west on a number line, that's great. Now, since you just asked about that B part on number 6, I'm going to do something hopefully kind of enlightening here, because when I asked you about number 6B, the way I answered it was saying, hey, the directions will be the same. And that's true. And that is one way to answer it. But let me draw a picture. Let me do this one again, but I'm going to do this. I'm going to draw a circle. And I'm going to pretend that the object is just kind of horizontal out. But I'm going to say, what would it look like a moment before here? Well, I guess it would be back a little bit if it was heading in this direction. And so let me call that the initial velocity. So see how the initial velocity is kind of angled a little bit? I say that because a little bit later, it's over here, which would be final velocity. And I'm going to use this technique of drawing arrowheads that I just showed you. If I were to draw the initial, it would head off at some kind of angle like that. And then if I were to draw on top of that, or I shouldn't say on top, I should say an extension of it, I would draw the final. So if this is the final and this is the initial, this part right here, I guess I'll do in green, would be the sum of the two. But let me make a parallelogram out of this. Let me draw final first, then initial. And remember, we just said if you were to draw from the end of the first towards the second, this diagonal is the change. And so I'm hoping you see that the change is towards the center of the circle. And that's what we came up with before, but we did it by saying the change would be in the same direction as the acceleration, and the acceleration would be the same as the force. And we used a little experiment to say the force was towards the center of the circle. But I think these pictures are kind of a step up, if you will, in 2 dimensions. And so anyway, hope I didn't say too much. I don't want to overwhelm you. You've got a test coming up here. And so
that was really good.
okay, and that's a little more than you need for the test, but for you guys, we do a lot of one-dimensional stuff. The other people looking in from 122, they're very familiar with all this. We do a lot of this a lot more of this in 121. But anyways, this is our step in that direction. So we draw arrowheads in just one dimension for starters.
Awesome.
Good. All right. Let me jump back here. I think again, Eli, you're the only one here from 121 102, sorry. 102 for the moment. So I will keep you on the fast track here. And plus I know these guys, they're 122 questions. We're going to be here a long time with these guys.
All right.
So
then I have a question about chapter 4, number 11.
All right, chapter 4.
Maybe it's not chapter 4.
Not chapter 4?
No, it is chapter 5.
All right, so chapter 5, number 11. Let me write that one on here. All right, so chapter 5, number 11. Let me scroll down here. Chapter 5, number 11, almost be in the other column. Oh, okay. All right. So this one says a 320 kilogram satellite experience a gravitational force of 800 newtons. What is the radius of the satellite's orbit and what is its altitude? Okay. So this is in the chapter on the universal law of gravity. And so maybe I'll begin with a question for you that, does this formula look familiar?
Yes.
Okay. Universal law of gravity. Okay. So this one actually doesn't say that you're going to have to do a little bit of looking up the numbers of the Earth yourself. I hope that comes across indirectly. But here's what it's saying. It says, all right, if you put in all these numbers, you will get a force of 800. Okay, so I'm just going to put 800 for the force. G is what we call the universal gravitational constant. And it's in units of newtons and meters squared and kilograms squared. And of course, not even mentioned in this problem, but in the reading is you need to know that. Now you don't have to commit it to memory because your test is open book, but you're going to need that number. All right. So then you have the masses. Now the two masses here are the two objects that are interacting, and this is the part that you maybe makes it hard. I don't know if you, but you're supposed to realize that the satellite is being tugged or pulled by the Earth. So one of the objects is the Earth, and so you need to look that up. What is Earth? 5.98 times 10 to the 24 kilograms. So there's the mass of the Earth. And again, I don't expect you to memorize it. I haven't memorized just because I have to use it so much, but look that up, okay? Now, the mass of the satellite is the 320 kilograms. And as a side note, notice I put in the mass of both of them in kilograms. And the reason I did is the gravitational constant is in kilograms. So my units will cancel off because ultimately, my got to put it here on the left-hand side, but the force is in newtons. And so in order for this formula to work right, mass needs to be in kilograms with this constant, and distance needs to be in meters. Okay. All right. So I'm just going to then put r squared here, because that is one of our questions. What is the radius of this orbit? And so maybe a picture could help out here. If this was the Earth, and so here's the center of the Earth, and I put some satellite up here. As the satellite goes around, then this right here is that distance r. That's one of the two questions. And that's perfect, because see, I have a nice little mathematical formula here that has a bunch of numbers and only one unknown. So I've got some algebra to do in order to solve for r. Now, I'm going to check my units here, but it looks like a newton on this side would cancel with a newton on that side. So if I were to move the r squared to the left-hand side of the equation, leaving my numbers, there's the gravitational constant. There is the mass of the Earth. There's the mass of the satellite. Now my units that are left are meters squared, which is actually going to be really good, because in a second I'm going to take the square root to get r, and then that'll mean units of meters. And then, of course, let me not forget to bring the 800 also over here. And so now I can grab a calculator and put in my numbers. So 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 320, and then divided by 800. So this is 1.60 times 10 to the 14 meters squared. So the final step of the first question, I should point out, is to take that square root. So I'm going to take the square root of all of that. And that means I would have the square root of the number 1.26, let's see, 1, 2, 3, 4, 5, 6, 7 times 10 to the 7. And then the square root of meters squared is just a meter. And so there would be our first question. What is the radius of orbit? And then the second one of this is, what is its altitude? Well, to answer that, let's come back to this picture I was trying to draw. It looks like this radius of orbit, so I'll say r down here, is equal to what? Well, it would be the radius of the Earth and then the altitude. So I'll put capital R for radius of the Earth, and I'll put capital A for altitude. Okay, so we just did this little r, 1.26 times 10 to the 7th. And this is the part that I was saying, for the Earth, like the mass of the Earth, we need to look in the front cover of the book, or back cover. I forget which one it is on your book, or actually it's easier probably these days just to Google it than to bother to open the PDF. But the radius of the Earth, let me think here, 6.37 million meters. And again, I don't expect you to memorize it. I just do because, well, I use it so much, but I also like to do those things. All right, so there's the radius of the Earth. All right, so this number is still in my calculator, so I'm just going to subtract 6.37 times 10 to the 6th meters and come up with an altitude of 6.26 times 10 to the 1, 2, 3, 4, 5, 6. So about, oh, interesting. It's about 1 Earth's radii. So
Got it.
it's that's pretty high. That's much higher than a near Earth orbit,
Yeah.
but not nearly as high as a geosynchronous orbit. So, I guess I'm just trying to think of a good engineering reason of why we would put it there. We usually do a near Earth to keep them close, or geosynchronous, so they match the spin of the Earth. Now the GPSs, we like to make a period of exactly 12 hours minus 4 minutes. I don't think that does it. So I don't know why we would want that orbit. Anyways, I'm tempted to get lost on the geosync orbits. They're a fascinating discussion too. But I'll pause. All right.
Awesome.
So
Thank you.
good.
That's
All
really
right. Well, let me go back to the chat. Anybody from 102 now? Like I said, you might be the only 102 person today because
yeah.
most of you took the test. All right.
Okay.
Got another one for me?
Yeah. So actually, let's see which one. So number 5 from the same chapter, from chapter 5.
All right. So chapter 5, number 5. So, chapter 5, number 5. Let me get a timestamp here. All right, 1042. Good. Let me switch back to this one here. All right. Chapter 5, number 5. Oh, okay. So here is a solid lead sphere that has a radius of 10 meters, which is it's huge, 66 feet across, has a mass of, oh my goodness, 57 million kilograms. If 2 of these spheres are floating in deep space and their centers are 20 meters apart, actually, let me start right there by just drawing a picture. So if they have a radius of 10, then these things are just in contact with each other. They're touching. Okay. And their centers then, I'll draw a little 20 meters apart. The gravitational attraction between the spheres is about 540 newtons, which is about 120 pounds. How large would the gravitational force be if the distance between the 2 spheres was tripled? Oh, I love this question because there is 2 ways to get there. I'll make 2 columns here. I'll call it step 1, step 2. And maybe I'll just write out one and won't complete it. The kind of the easiest one to think about is to say, let's write that same equation, the universal law of gravity that we just were working with, and let's put in our numbers. So we would have 6.67. Oh, can't really write all that on one line. My bad. Let me put number 1 down here so I have more room to work with. So 6.67 times 10 to the negative 11 is the G. The mass of them is the 57 million. Now, if you'll go ahead and just let me do a little less writing, because remember, it's mass 1 times mass 2, and these are identical objects. So I'm just going to put a square there and save myself a little bit of writing. And it says divided by the distance between them. Now, they were originally 20 meters. And so they say, how large would the gravitational force be if the distance between the center of the two was triple? Well, tripling means they're now 60 meters. So I'm going to put 60 and square that. Now, I deliberately left the units off so I can kind of put them by themselves. Remember, the units for the gravitational constants were newtons and meters squared over kilograms squared, which is to remind me that you should always put your mass in kilograms, good, and they gave it to me, and distance in meters, good, they did. I don't have to worry about changing it. And then, of course, I'm going to come out in units of newtons. And then I'll just do a number. Now, I'll go ahead and just put that number in here. 6.67 times 10 to the negative 11 times 57 million squared divided by 60 squared. And if I put all that in there, I come up with a force of about 60 newtons. All right. Now, I would say that one is probably the easiest one conceptually.
Yeah.
Because it's just kind of a direct plug and chug. But watch this. There is another way to do this that I'd call maybe a level higher. Okay. Because they actually gave me some very useful information. They said, if you took the two masses and divided it by the r squared original, this is the original r, okay? The original 20 meters. If you actually did that, I'm not going to actually do it. I'm just going to say, if I did it, they're telling me you would have got a force of 540 newtons. Okay. So without putting in these numbers, they're telling me that's what I would have got. All right. Taking them and trusting them on their word, watch this. If I now increase their distance so that it's 3 times bigger. Okay, so I'm going to put a 3r squared. Of course, if we actually put in the numbers, we would be saying 3 times 20. That's if we actually put in the numbers. But let me not put in the numbers, and here's why. Because if you then just do a little bit of math, and that's why I'm saying this is maybe a little more advanced. Because if you remember from your algebra class, when you exponentiate something, you have to do both terms. So if I have 3r squared, that is the same as an r squared and a 3 squared. Well, a 3 squared is just a 9. And all these numbers, if I put them in, is supposed to come out to be 540. So this is really 540 divided by 9. And of course, 54 is 6 times 9. So the 9s would cancel, and you would have 6 times 10, and you would be just left with 60. Yay! So
Wow.
And so I would call this the advanced way. So if you saw it, great. If you don't see it, that's actually fine too. That'll come in other semesters, but that second way is nice to show. It is considered a little more advanced, if you will.
Awesome. That was cool.
All right, Eli. I'll do one more before I think I'll if you have another one, and then then I'll swing back to some of these other ones and come back to you. Okay.
Yeah, fine by me. All right. Yeah, I got one more.
Oh, and if you only have one more, that's better still, huh?
Yeah, that should be good enough, I think. So,
Okay.
number 10 in chapter 6.
Okay, so chapter 6, number 10, and we're looking at a time of 10:50. Chapter 6, number 10. All right, now also let me point out here that, one of the clues I like to tell students when they're asking questions in number 6, it's about momentum. If you ever see a problem of things colliding or interacting, that's probably a clue that it's a momentum problem. So I just going to say that to see what number 10 actually says here. But it says here, a coach is hitting pop flies to fielders. Okay. So this, probably is not a conservation of energy. Maybe it is. If the baseball, they give the mass, stays in contact with the bat and leaves the bat at a speed of what is the average force? Okay. So they're not looking at the two objects, which would be the bat and the ball together. If I ever saw something like that, that would be a conservation of momentum. This is a separate one that is basically saying this, that in chapter 4, we said force was equal to mass times acceleration. But there is another way of looking at that. Acceleration is change in velocity over time. And mass and velocity if I put them together would be called momentum. Or let's see. And do they give momentum or do they give mass and velocity separate? Okay, so I'm going to leave it this way. But the book does write it as change in momentum over time would equal force. And then, of course, momentum is mass times velocity. And for this problem, that's what we have. So this problem says, what is the average force? So I'm going to solve this for force. And so the change, and maybe I should write it this way. I'll put the mass of it. Now here, I want to be a little careful with my units because they gave me the mass of the baseball in grams. And normally we like to list force in newtons, and a newton is listed in kilograms. So let me do a little bit of conversion and take that 145 grams and move the decimal 3 so that I have 145 kilograms. So there's the mass of it. Then I'll do the final speed minus the initial. Now it says it leaves the bat at 50 meters per second. Good. Initial, here's where you got to kind of read into this. I don't know if you've ever played baseball or watched a coach hitting it. They just stand there and they toss the ball up with one hand and hit it with the other. So it's not like a baseball game where the pitcher is throwing it at them. And so there's a large initial speed. And then there is a large final speed if somebody hits the ball. In this case, the coach hits the ball. So the final speed is 50. But I think they want us to read it as, hey, the initial speed is really small, maybe 0. Maybe even the coach puts it on a tee, and puts it down and hits it off the tee. And I got to admit, the question could read a little better because, what is the initial speed can be open for debate. Probably would read better if it said the coach was hitting pop flies off a tee to outfielders, and so, oh yeah, they're setting it on the tee. The initial speed is 0. You have some kind of evidence to support what the ball is doing before contact. But the normal play is the coach just kind of lobs it up, hits it off that. So it has a very, very small, near 0 initial speed. So the author could have done a better job there, but I'm going to put a 0. They gave us the time. The ball is in contact of 0.04 seconds. And so let me look at the units first. This would be a kilogram times a meter per second each second. Well, that's the definition of a Newton. That's perfect. Going to come out in force in newtons. And then let me grab my calculator, 0.145 times the 50. And 50 minus 0 is a 50. Okay, so won't worry about that. Then divided by 0.04. And looks like at 181.
Awesome.
Oh, and hey, by the way, I just dawned on me. Do you know that the solutions for these are posted also?
I was having trouble finding them.
Okay, let me send that right now in the chat for you.
That would be pretty helpful.
Yeah, let's see. I was wondering if it was on this first email. So the first email I sent you, it sounded like you must have got, because you got the homework set and you got the lab manual and the textbook. Oh, it's a little higher up in the reading. Here's the link to check your homework. Let me copy link and put it here in the chat. There we go. So either way, go back to that first email that had your homework assignment, or
Nice.
I guess it's also in Canvas in the announcement, but that's easier right there in the link in the chat.
Cool. Thank you.
All right. All right, Eli, I'm going to move on to a 122 question, but feel free to hang out or feel free to come back later in the day and follow up.
Yep. Thanks.
Okay. All right. All right. Hey, there's James. Good. I'm glad you said you had plenty of time to do other homework, because that was a little longer than I anticipated, but some really good questions. I'm glad that I don't have. I've got a lot of 102 answers. That's going to help a lot of students. 102. All right. So let me switch over to your question, James. So we're looking at chapter 26, number 7, and we are at 10:58. Okay, so chapter number 26, problem number 7. And I don't think I've called up your guys' homework yet today. Let's see. Actually, let me move things around so I can see my tabs better. Okay, so yeah, so there's 102. Let me come over to your class. And where's my welcome email? Here it is. And here, okay, so here's the homework. Nice. And let me move that tab here. Oh, nice. And actually, your guys are pretty involved here. Let me also call up the solution. Ooh. Good. I got an error for said site couldn't be reached, but there we go. All right. Because you guys, I'd like to check the solution before I say I'm done with it, just in case there's a different approach or did it wrong or something.
Yeah, I can, my solution, like my question, maybe don't have to work through the whole problem.
Okay.
If you go and pull up the, like the answer guide.
Oh, okay. The answer, not the question? Well,
Yeah.
let me read the question here. When a potential difference of 150 volts is applied to plates on a parallel plate, the plates carry a surface charge of, what is the spacing between the plates? Okay. Okay. All right. And then the answer they give is charge equals. Okay. What's your question on that?
So we've got distance is the permittivity of free space times the voltage divided by the area charge density. And
Okay. Yeah.
getting there is okay. Like I got there too. That makes sense to me.
Okay.
But
Good.
then in the denominator, an area term shows up. And that's odd to me. And
Oh, wait. I think you're confusing an area with a unit conversion or something.
okay.
So they give the 30 times 10 to the minus 9 coulombs per square centimeter.
You know what? That's it. Okay, cool.
Yeah. And then the other factor is converting square centimeters to square meters to match the units for the permittivity of free space.
Nice. Okay, awesome.
Okay. Yeah, that one wasn't as hard as it seemed, huh?
No, that's good. Okay. I was like, what? Like, and then I just totally didn't realize it was given in centimeters squared. I have another question that might be pretty quick too.
Okay.
So the same homework, question 19.
All right.
I gotta go grab it actually.
To 19.
Yeah. Okay, so
Uh, 19. Oh, yes. This is always a interesting one because you can't just simply plug and chug a bunch of numbers in here. You kind of have to understand what's going on when the switches open and close.
yeah, okay. So let me see if I got, because it's always, I'm so bad about like causality and then the text and like, okay, so we close switch 1, right?
Yeah.
We charge up C1, switch 2 is open, so C2, nothing's going on over there.
Right.
And then we open switch 1 up again,
Right.
taking the battery out of the picture, I think. Because
Okay. Yes. I'll say yes. But also let me.
Right. Is that? Yeah. Sorry.
Well, let me add one other thing. When you open switch 1, not only do you take the battery out of the equation, you also, because of conservation of charge, lock in the total amount of charge. So
Okay, I buy that.
Okay.
I do. And then we close switch 2.
Mhm.
And I worked it out the way the instructions say, and I can see how, but I tried it again today because I marked this one to go back to because it was one I struggled with. And I treated it as a series arrangement, but the solution assumes a parallel one, I think. Like if I think of these capacitors as in series, then I say Q1 equals Q2, which obviously isn't what we get.
Yeah.
But they kind of, I mean, maybe it doesn't mean anything to say in series if we don't have a battery in the picture. So that's my confusion.
Yeah, I see where you're going here with this. Let me try to show you why I guess it's not series. Okay. So series, as you said, has the same charge. Okay. But a series then, if I'll just draw it horizontally, says something like this. If I were to put 2 electrons that come onto, I'll call this the left plate of number 1, they then chase off 2 electrons from the right plate of number 1. So this always happens whether a capacitor is in series or in parallel. And so we always say that the magnitude of the charge on the left and right plates are the same in a capacitor. Always. It doesn't matter what else goes on. Okay. And I think you know that. You weren't even questioning. Okay. But in series, then, watch this, that then this over here is where those two go. And so I'll call this the left plate of number 2. And it's because of this connection that we would say that the charge on number 2 is always going to be the same as the charge on number 1. And of course, let me not forget that 2 electrons would be chased off of the right plate of number 2. Okay. And then, of course, for these to get chased off, there does have to be something else for them to go to. Okay. And so I'm just drawing a piece of it. But so that's series. Here's where you're going to get into trouble. If you were to just look at that, but take this and wrap it back onto itself, the leaving of these then affects those, which affects back onto this. So that's where the kind of the series thinking breaks apart.
So the battery is like a reservoir that's just like kind of taking the ones that are leaving, and is that?
Yeah.
Okay.
Yeah. So it had these, let me cross this out and put it to a battery, as you said, negative plus. The battery is kind of this reservoir of electrons. It has these redox reactions going in. I'll just say it's, one of the standard car batteries, lead sulfuric acid. And so the reaction with the lead and the sulfuric acid puts our electrons, lets them come out and lets them come in. And it's a reservoir. It will make as much chemical reaction in here as needed to fill these up, because this, there's a lot of sulfuric acid in here and lead. And so a reservoir is a great way to describe this. And so that would be a series, and that's how a series would work. But once you take away that battery and connect it back onto itself, in fact, if you didn't connect it to anything, you couldn't get this to even happen. You couldn't even get anything to flow because this couldn't flow off. So if you just had 2 capacitors sitting there without a battery, I'm not sure I would call them series, because I can't really do anything yet. And if you hook them back onto themselves, again, I would not call that a series. So once you hook them back on themselves, then what they do is they push and pull each other until they're equal. And so one is pushing, one is pulling, and when they exactly balance, that's what we mean by the potential being balanced. And so I would describe these a little bit more as being in parallel. Again, I might even stay away from that word because they're not hooked to a battery, so they're not like having the same charge, but they do have the same voltage as each other, and they push and pull on each other and shift the charges around until they have the same pole, not the same charge. So they really are more of a parallel behavior than they are a series behavior.
I think I'm going to prefer to categorize them as their own thing, because
Okay.
I can. No, it's okay. Yeah, but it is like parallel, but I can see how the voltage would equalize.
Yeah.
So I could then say V1 equals V2, and
Oh, you know what? I'm going to try this. This analogy worked with you one time really well, so I'm going to try it again. Let's say I have water and I have this giant reservoir, and it's filled up to this level. And I then have a pipe that connects to a container. Let me call this capacitance number 1. And that actually then, flows from number 1 into another capacitor, let's say number 2. So tank number 2. And if these have valves in them that I can open and close, if I were to open this first valve, what would happen is the pressure would fill up until it's the same level as the reservoir. And that's kind of like this battery. But then if I close this valve, I would be disconnecting the battery, I'd be disconnecting the reservoir. And if I open this valve, what's going to happen is this one goes down and this one goes up until they're the same level. So they don't necessarily have the same amount of water in them. And number one doesn't have the same amount of water it had when it was first filled up from the reservoir. It went down, but the level here, the pressure, and in this case, the voltage pushing back and forth is the same.
That's awesome. Okay.
Okay, well, I'm glad that one worked too. Yeah, and again, probably not a good idea to call them either series or parallel. It's probably just better to look at, okay, what's going to happen here? Are they going to push and pull until what? And so this case, I would say charge shift around, not until the charges are equal, but the pressures are equal.
Solid. Thank you, Professor.
Good. All right. All right. Hey, let me jump over here to the chat room. Let's say, Sasha, you said you had a question, but you didn't write anything down, but I won't pass you up just because of that. But
yeah, I didn't write anything down, but I did have a question. It wasn't anything specific, I guess. So this past week, I was actually really busy with a lot of other classes. Okay. And so I haven't actually had any time to sit down and like start real studying for the exam. So that's what this weekend is probably going to be for.
Okay. Fair enough.
Yeah, I mean, I'm not behind on the homework or anything because okay. I finished it all every week. Like I told myself like by Sunday I would have all the problems completed. So like okay. At least I didn't have to worry about that. But so now I just like want to make sure that I'm prepared for the exam. And I guess I'm just thinking about some good strategies for tackling how I should I go, okay, start today, chapter 23, tomorrow, chapter 24, day after 25, or maybe something kind of like more based on what yeah, I'm not sure.
I like to tell students this: once you've done all the homework, which you have, and you're getting ready for the test, the next step is that practice test that I sent out.
Okay.
And I don't know if you've done that, but I would sit down and don't look at the solutions yet. Yeah. Okay, so the practice test comes with the solutions. Just try them. Okay. And see how well you do on that. Also time yourself because you're looking at 25 minutes a problem. Now that's average. So hopefully some problems click a lot easier with you and you go, okay, I did that one in only, 15 minutes. So I've got, some 10 extra minutes on another one that, is going to challenge me. And that's kind of why I always encourage students. I said, when you take the exam, maybe, already start off the idea with 5 pieces of paper. You're eventually going to take a picture of those 5 and send them up. But if you read that first one and it looks like it doesn't really click with you, move on to the second one and go, okay, and find the ones that click with you. And so nail those down, and hopefully, hopefully 3 of the 5 click right away, and so you're, 15 minutes each, you're 45 minutes into the problem and you got 3 of them done. And you're like, okay, good. That means and you can do the math from there and say, okay, now I don't have to stress about these other 2. I've actually got 42 minutes each on these other 2. Okay, good. Anyways, and so work your way through those. And if you're really fast at scanning them, you even have a little more time than a face-to-face class would have, because I'm giving you 25 minutes to scan it and upload it. And truth is, not going to take you that long if you have already done it. Actually, a side note, one of the annoying things, students is they're so, they go, "Oh, just a little bit more, I'm almost there." And, and they only save themselves 2 minutes to upload it, and that won't happen. So anyway, that's a side note. But I would say back to that, do that practice test. And that'll give you a clue of where you are. It'll also probably give you a little more clue on what areas you should work on, because that practice test has the solutions worked out, both on the PDF and on the video. And so I would encourage you to go through the solutions and the videos, even if you felt like you got it all right. Just go through them. It's a good learning experience. And then if you've got more time beyond that, well, if everything went well, you probably really are ready for the exam. But most people feel like they should spend still some more study time. And so
Yeah,
I would say now, if you felt weakest in, and let's just say chapter 24, then what I would do is I would go to the problems in the book, go to the PDF, go to the problems at the end of chapter 24. You'll see where in the problems, they have the first part of the problems, they're broken down by sections. So if you happen to know what section you were weak at, you might want to do the ones from that section. Now, most people don't know what section they're weak in. They just know, hey, I'm not real good with Gauss's law, and that's what chapter 24 was all about. So go to the part that towards the end of the problems that says just, how does it say? It says something like
additional problems.
Yeah, additional problems.
Yeah.
Because those, you have no idea what section it is from chapter 24. And it also pulls in old material from like physics 121 and chapter 23. And so those are really good ones to practice for the test, because you won't. And so I would look at them and say, all right, let me try one. And if you're looking at the PDF, I would try to look for a blue one, because a blue one is a pretty hard one. Now the magenta one.
Yeah, I was about to say not the pink one or whatever, because those are like the hardest.
Now those are the hardest. I guess I would say the magenta ones, try to do them, but don't worry about doing them in 25 minutes, because they are the hard ones. I mean, if you can do a pink one or magenta one in 25 minutes, great. Consider yourself, on a good path to being ready for the test. But at the same time, I would say to be ready for the test, you should be able to do a magenta one, but not necessarily in 25 minutes. Those are a little too hard to put on a test, because they do take more than 25 minutes. I try to shoot for ones that are more blues, so that they're not the easy black ones. But try some of those too. Try the black ones, and just know that hey, this is supposed to be an easy one, so you should nail that one in under 15 minutes. But and that'll give you some idea. And then the blue ones should take you probably about the 25 minutes. And the magenta ones, like I said, you should be able to do, but if you do it more than 25 minutes, that's nothing to be concerned about. You're still on track there. So, like I said, if you can figure out what area, I would start there. And so, do a few of those till you feel like you've gained some knowledge and some strength. That's good practice. And then if there was another chapter, shift over to chapter 26.
Cool. Yeah. So maybe once I try tackling the the previous exam on my own with no resources, just like as if I were doing the test, and then I can evaluate where I'm at. If I see some weak spots, maybe would you say, if this is even possible, to like search out for some problems that are similar in style to maybe like the problems that you ask for on the exam, or are they kind of different, or similar?
Hard for me to answer that. I'm not really going back to old exams and seeing, okay, what do I did before, and trying to match them or trying to dismatch them. there is some kind of universal stuff like, Coulomb's law, so the big picture. So you're going to get something like Coulomb's law. I'd see somebody asked me one on the practice test, and so on the practice test, there must be one that has like a quarter circle. And so that's Coulomb's law, figuring out what the electric field is at the center of a quarter circle. But problems like that would be on the test, but they may not be a quarter circle. Now they even may be a half circle, but it may be something, very different in the sense that it may be charges in a straight line. It may be some kind of combination thereof. And so maybe 2 half circles, there would be an interesting one, So the idea is, well, you do really a half circle, but you've done that, you do it twice, maybe 2 quarter circles, maybe 2 straight rods, but at 90 degrees. And, so there's a lot of variances that can play off it. So what I am saying is, if you see something on Coulomb's law, then yes, practice more Coulomb's law, because yes, there's definitely going to be something like Coulomb's law, but whether it's going to be a quarter circle or a half circle or something straight versus something round or something more 3-dimensional than 2-dimensional, that's open. That's just whatever problem I kind of come up with and design in my head, which would be Monday. So.
Right.
And
Yeah. So
not,
maybe then like pull out some general idea, like, okay, I have an issue with like finding Gauss's law or something like that, and then you work from there or something.
Oh, right. And there's another good example, because there's problems to do Gauss's law that, you've seen that, have cylinder shape objects and maybe cylinders within cylinders. But we've also done problems that are spherical in nature. And spheres within spheres. We've done problems with Gauss's law that are like a sheet of charge. So they're more planar in nature. And so again, depending on how you look at the test, if you see the test question as using Gauss' law to find an electric field, then yeah, that's what you're going to see on the exam. You're going to see an exam of, hey, you need to use Gauss's law to solve this. But if you see this as a problem involving a cylinder, and I can't remember which one's on the practice exam, and you only practice cylinders, there's, a 1/3 chance that it's going to be a cylinder versus a sphere or versus a plane, and maybe same thing as before. If we did 1 plane, maybe we can do 2 planes, or we did 1 cylinder, maybe we can do 2 cylinders, or maybe 2 cylinders at right angles to each other. So we think about it, as a cylinder one time, and then we double it, and then the angle for the electric field. So there's a lot of variations that can show up. That's why doing those magenta ones are good, because that's kind of what the author will do. The author's focus is to say, let me give you a bunch of different problems that involve Gauss's law, not just cylinders, not just a 1 cylinder. Maybe it's 2 cylinders. Maybe they're parallel cylinders. Maybe they're right angles. Maybe they're spheres. It's like, oh, okay.
Right. So yeah, that's good advice. I would say that if I could take something away from that, study the concept, not
right. So
just
in
the
words,
particularities.
Right. So in words, I guess I would say know that the big picture of chapter 24 is Gauss's law. So you're going to have a problem on Gauss's law. That's the big picture. But the geometry, you don't know. And so try a bunch of different ones. And the chances are there's so many that the one you actually get on the test is different than any of the ones you practiced. So it's not about finding the right one so that you know it when you come into the test. It's about the, as you said, the general overall principle of Gauss's law.
Cool.
And same thing with Coulomb's law. And same thing with potential. And same thing with capacitors. So, I mean, really, you could summarize the test that way. There's going to be a problem on Coulomb's law. There's going to be one on Gauss's law. There's going to be a one on potential energy, and there's going to be a one on capacitors. Now, whether the capacitors are series or parallel or some combination, whether it asks for voltage or charge, I mean, none of that you'll know. You try a bunch of different ones, but after you try 10 of them, hopefully that puts you in a spot where you could do any of them, because that there's hundreds of thousands of different problems. You can't do every problem, and you got to do 10 of them with the idea that, okay, now I've done a bunch of problems like this, which have capacitors in series and parallel, so I know I will get one like this. The chances of it being one of the 10 that I already did are very slim, since there's hundreds of thousands of problems. But whatever one I get of those hundreds of thousands, I can do. That's really what you want to get yourself in the position.
Got it. Yeah. Thank you.
Good. Yeah, great question. All right. So I see why you didn't try to type it out. So good. Wasn't a particular question. All right. I'll go back here to the chat here. All right. So who do we have? All right, Johnny, you are asking about chapter 26, number 23. 11. Wow, it's already 11:27. Well, let's make sure we do this one. It'll take us into our break, but it'll be worth it since it's up here in the chat. And I guess I've been talking a lot here. All right, so chapters 26, number 23. Let's give this one a shot here. What am I doing? Okay, so let me find chapter 26 here. Okay, got it. Number 23. 23. Find the equivalent capacitance of point A and B in the group of capacitors connecting as shown. Take C1 to be 5 microfarads, C2 to be 10 microfarads, and C3 to be 2 microfarads. All right, so let me draw a bunch of equivalent circuits. I'll start right here. Here's point A, and it looks like A comes in and it can go to capacitor number 1, or the charge can go to capacitor, well, I shouldn't call it number 1 because that's a C1 also. But I guess I will start by saying that these 3, if we were to say, hook this up to the negative of the battery. If we hook this up to the negative of the battery, charges could go to, I'll call it the left one, the right one, or the middle. Because of that, this is not series. But also, these are not in parallel, or at least not in parallel with themselves. Because to be in parallel, we have to be able to connect both ends of them without anything in between. As you guys probably saw in the video lecture, sometimes I like to color code where my colored markers go. And as I color code them, if you can, say, all right, I can draw this in green. And so these are all connected with a wire. So these all have the same potential. And the other side, maybe I'll do kind of a purple color here, of number 1 doesn't go all the way back to the other side of number 3, and it doesn't go all the way back to the other side of number 1, or the right one over here. So this left one is not in series, but it's also not in parallel with either of them. So I would say this situation right here is neither series or parallel. yet. But let's keep analyzing, because this comes back and connects here. So this is C2, and then this even comes down and connects before we get to point B. And these are each a C2 and a C2. All right, well, here's where the magic begins. These two bottom ones are in parallel. And again, one of the ways I like to do it is say, okay, if I connect and I'll say the left one here in the bottom with the right one, because those are connected with a wire, those two have the same potential. And I've connected them with green. Now, can the other side, I'll do this in purple, of the left one be connected without anything in between? Because if there's something in between, it would change the voltage. And it can be. And so I would say the left one, the potential difference is from green to purple. Well, the right one is green to purple. I should do violet. Purple's not a good science term. I don't know if you ever watched The Magic School Bus when you were younger, but there's a great one in there about color purple. So if you have extra time, which you won't this weekend because you'll be studying for the test, go to YouTube. I think all those Magic School Bus ones are accessed on PBS or on YouTube, something like that. Anyways, they have a food fight in the whole cafeteria over the argument of purple. So it's a fun one. Anyways, shouldn't call it purple, but I should call it violet. Anyways, but those would tell me they're in parallel. So the equivalent of those two is to add them together. So in a moment here, I'm going to replace those two with C2 plus C2. So that would be 2 C2. Now, let's come back up here because there is some little work I can do here. Right here these two on the left and these two on the right kind of do the same thing. Notice that for this top one on the left, it is directly connected with no other place to go but to the C2 that's here on the left. And if I can draw a line, this is in violet, that goes from one straight to the other without ever coming across another intersection or a node. That means all the charge from this C1's got to go to this C2. And that's what we mean by series. So I would say this C1 and this C2 can be combined together in series. Now, series, the formula looks like this. It's a little harder. We have to add reciprocals. So I'd have to have 1 over C1 plus 1 over C2. So let's see, C1 was a 5, and a C2 is a 10. Looks like that's a common denominator of 10. So it'd be 2 plus 1. So that's 3 over 10. So when I take the reciprocal, I get 10 over 3. All right, so I can do a replacement there. And notice that the same logic applies to the right-hand side. That if you were drawing, and I'll do this in blue. I don't know if blue shows up on your screen different than the violets, but maybe I even should have done it in the violet just because it's the same connection. But everything from this C1 on the right goes to this C2 on the right. So those two are in series, and we would add them exactly like we did to the ones on the left. And so I can replace that. So my first thinking here is to say, okay, this is the real circuit. Never forget, this is the real circuit. But the behavior of that real circuit would be the same as this equivalent circuit, where this one here is this 10 over 3 from the combining of the C1 and the C2. And this over here is a 10 over 3, which is the equivalent of these two putting here. And this one down here is the equivalent of these two, which we said was in parallel, which is 2 times C2. Now, C2 was 10, so this would be 20 microfarads. So that's 20. Now, I should probably put in the number for this middle one, which is C3, which is 2 microfarads. So I'll just put a 2 right there. And let me call this page 1. So that's kind of the first thing to do, is to find out some equivalencies. So I'll say it again, this circuit is equivalent to that one. All right. Now, is this equivalent to? In other words, is there an equivalent to our equivalence? And yes, there is. So page 2, I would say, all right, let's look here at the equivalent circuit and see if we have anything that would be equivalent. And I'll call it the equivalent of the equivalent. So yeah, it looks like these three up here are in parallel. Now, not only visually are they in parallel, but as I was saying, one of the ways to see if something is in parallel is to say, if you connected the two together, okay, so I'll call this the left and middle. Okay, so the left and middle are connected. Let's look at the other side. The other side, I'll draw in violet. Can I go from the left one to the middle one without anything in between? Because anything in between would change the voltage. And if nothing's in between, then that means the voltage from this left one across it from blue to violet would be the same as blue to violet. And so, yeah, it is. So I would say these two, the left and the middle one, are in parallel, and the same logic would apply to the middle and the right. And so this set of 3 are all in parallel. So I can get the equivalent of that. So there is an equivalent to my equivalent. Now, I'll be careful to point out that this one down here, it's 20, which was the equivalent of the 2 C2s, okay? Then this one here, I would have to say, at least the way it's drawn right now, is not in series and not in parallel with this, with any other one up here. So I can't combine this with it. And I'll say that, well, at least not yet. But I can get the equivalent here. And of course, they're in parallel, so you just add them together. So this would be a 10 over 3 plus a 10 over 3 plus a 2. I guess that's a common denominator of 3. So that's 10 plus 10 plus 6. And so I have 26 over 3. Did I do that right? Yeah. So I can then say, all right, let me draw point A, and let me draw an equivalent capacitor, 26 over 3, which represents the equivalent of these 3. Okay. And so I'm going to call this the equivalent of the equivalent. And then finally, I'm going to ask now this one, which this one is equivalent to this one, which is equivalent to the top one up here. So all these are equivalent circuits and capacitors. Is anything equivalent to that one? And so this is the one that, again, hopefully you can see. And if you take this top capacitor and draw a line, it goes straight to the bottom capacitor. There's no place else for it to go. There's no node, no intersection. So these two must be in series. So the equivalent of this circuit. So let me say already that this is the equivalent of the equivalent. So there will be the final step here, which would be the equivalent of the equivalent of the equivalent. Okay. And then, of course, I have to add reciprocals. So it's the reciprocal of this top one, which 1 over 26 thirds plus 1 over 20. And maybe just because I don't want to deal with fractions here, I'm going to, well, I'll write the 3 over the 26 and the 1 over the 20 and add them together. So 3 over 26 plus 1 over 20. Now, that is equal to the reciprocal of the equivalent. So to get the equivalence of all of them, I need to take one more mathematical step. Take the reciprocal. And so all of these together are equivalent to one capacitor that has a capacitance of 6.05 microfarads. And so I think that's the question. Find the equivalent capacitance. And let me see if that agrees with the author. Yeah, 6.04 is what the author writes. Nice. So we've got to do a bunch of equivalents to keep breaking it down. And hopefully we don't run out of equivalencies. Notice that, by the way, I could not put the 1 and the 3 together at the beginning, but ultimately I could. Because once I put the 1 and the 2 together and got here, then I could put the 3 together with those. And so sometimes getting the equivalent circuit is a multiple step process. You have to say, well, the equivalent of the equivalent of the equivalent of the equivalent. And I should point out that sometimes we leave the impression that you could always get an equivalent. No, sometimes there just is no way to simplify it down. Give you an example. Called this point A and this point B. We could put the 2 on the left as a series and the 2 on the right as a series, and that'd be the equivalent. And then those would be in parallel. And so we could get the equivalent here. But as soon as you put one across here, that one fouls everything up. It no longer allows these to be in series, and these are not in parallel like they would be if this was a wire connecting them. So you don't have series, you don't have parallel, you have neither, you're stuck. And therefore you need other techniques. And we haven't got there yet. So just know that everything we've done makes it look like the world can be simplified into series and parallel. But I like to say, ask yourself, is it series, parallel, or neither? And if we get to neither, we need to do different techniques. And that's why we have different techniques. We just haven't learned them yet. So I won't worry about them now. Those will come after exam 1. We will introduce resistors and kind of play the same game for a while. But neither is a possibility, but not yet. Not for you guys. Everything will be series and parallel for now. All right. Hey, well, I hope that helped, Johnny. And I don't see any other questions there in the chat. So this might be a good break time. And we're a little past our 11:30, but let's take a little break and I'll come back at 12:30 and we'll do some more. So hopefully I'll see you guys here.